This is the final video for chapter 8. We'll have a little bit more examples. We went through example 3.3 rather thoroughly. And by the way, here's a comment. We did all those for alpha equals to 0.02. And my challenge is to repeat this problem for alpha equal to 0.05. You can do that. Now let's move on to the next example. One of the best indicators of baby health is the weight at birth. In the United States, mothers who live in poverty generally have babies with lower birth weights. Although the average birth weight for babies in the United States is about 3,300 grams, the birth weight for the babies of women living in poverty is 2,800 grams with a standard deviation of 500 grams. Recently, a local hospital introduced an innovative new parental care program to reduce the number of low birth weight babies born in the hospital. At the end of the first year, the birth weights of 20 randomly selected babies were collected. All of the babies were born to women who lived in poverty and participated in the program. The mean birth weight was 3,060 grams. The question posed to you, the researcher, is: has there been a significant improvement in the birth weights of babies born to poor women? Set up the hypotheses and test them with the significance level of 0.05. Let's do it. Set up, well, we already did it in previous problem. We compare that with average for the women living in poverty, 2,800 grams with standard deviation of 500. And then what was the sample's value? 3,060. And also we want to look for improvement. So that's how we get the alternative hypothesis, where mu is significantly bigger than 2,800. Here are other data. Okay, let's begin with an initial picture. We have to draw a normal picture, and that is centered always around the null of 2,800 in this case. Well, here it is. Null value is 2,800. And then 2,060 is bigger, so we are looking for this right-hand side wing part. And the level of significance is 0.05 or 5%. That gives you this threshold or critical value. And we are going to find out this critical value. And finally, we'll compare that with the sample mean of 3,060. Okay, so how do we do that? Z-score is end minus center over standard deviation. Oh, excuse me, not standard deviation, standard error, isn't it? It should be. So in this case, x minus mu naught, 22,800, everything is approximate, so I need this one instead, over the standard error. But what is the standard error in this case? What is the setup? Standard deviation of population is 500, but sample size is 20, so this should be sigma over square root of n. It should be sigma over square root of n. And what is n value in this case? 20 babies. And sigma here is 500. So that should be approximately equal to this alpha value associated to 0.05. But if you look up 0.05 in the normal table, you're going to get a negative value because 0.05 over here in the left-hand side will give you appropriate z-score. Here 0.05 in the right-hand side, which means this blue part has 0.95. So look up the normal table and let's go for 0.95 in the second page. Where is 95? Well, here we go. 0.9495 versus 0.9505. The answer must be somewhere in the middle. 1.64 and 1.65. So let's estimate as 1.645. So 1.645, positive 1.645. Solving this equation, we're gonna get x is approximately equal to something. We can find out. That's gonna be this threshold value, critical value, with which we will compare 3060. Well, here's the full computation. Well, here I just use 1.64. Yeah, that's okay. And then calculating, I get 2,983 something. And that's the critical value. And 3060 is actually bigger than that. And putting everything in a single picture, we get something like this. 2,983, approximately speaking, and consequently 3060 falls into the red area. So what does that tell us? We have to accept the alternative hypothesis. In conclusion, there has been improvement. You see, null hypothesis is, as always, no change, same as before, status quo, and alternative hypothesis is challenging that. There was significant improvement. We ended up with red region, so we have to select alternative hypothesis, which means there was improvement. The new parental guide success, the new parental care program was a success as far as the level of significance of 0.05 was concerned. Now here's another challenge. Repeat the problem with alpha value 0.01. What happens? I don't know. It may be still alternative, or maybe in this case null. You can find out. Now let's redo the problem using an alternative method. Or those method in 8.4, the probability value approach, The same setup, and here is the initial picture. We do not look for the critical value, but we just go right ahead with 3060 and find out the area beyond 3060, this red area. And then look up the z-table, calculate the z-score, look up the z-table, and then find out this probability. And if this probability is bigger than alpha, then null hypothesis. Smaller than alpha, then it's gonna be alternative hypothesis. Why? Bigger than alpha means there is relatively large probability that something like this can happen when null is right. So, in short, there is big probability that null is right. If you snip out the middle part, that's how logic is working on. Okay, let's go ahead and find out z-score. 3060 over that I wonder if this computation is really correct or not. 3060 over 200,000. Okay, it should be 2.33 approximately speaking. Not the previous figure because I mistyped and then typed 3050 instead. Sorry about that. Okay, if it is 2.33, then what does the normal table say? 2.33, 2.33, which is 0.9901. So let's see, 1 minus 0.9901, 0.0099 approximately speaking. Okay. In any case, the same conclusion, less than 0.05. Consequently, probability P is less than alpha. What do you mean by probability value is less than alpha? This probability P is, roughly speaking, the probability that null is right. And the probability that null is right is less than this threshold, which means null must be wrong. And consequently, we reject null and accept alternative. The complete picture is coming as follows here. Okay, we have a little bit different p-value because we use a little bit more accurate z-score. Here, this z-score over here is 2.3255 something, and I will round it off to 2.33 and then look up the z-table. Consequently, we ended up with 0.0099 something. But if you use a little more accurate value, then you're gonna get something like this, but this is pretty close. In any case, far less than 0.05, so we are safe. Which method do you prefer? Do you prefer this critical value method that we did as solution 1, or the probability value method that we did as solution 2? Well, personally, I like the classical approach better, easier to understand, but a lot of people prefer probability value approach, but be careful about that. In some cases, you may end up with a value, a z-score, going out of bound, and it does not appear in the table, and then maybe you may panic. In that case, that means the p-value is really small, so small that it doesn't even appear. Another case, this probability value approach cannot be extended very well toward chapter 9 problems. That's a big problem, as a matter of fact. And for that reason, I'm emphasizing the classical value approach and solution 1 a little bit more than probability value approach. Let's see, do we have enough time for two-tailed test? No, I'm gonna just leave this one to students. It's not that important anyway. And that concludes chapter 8.